In this lesson, we will delve into the design of drilling and boring process plans and the analysis of typical cases in Project 3, focusing on the machining of whole systems in typical box components. As you all know, in the field of mechanical processing, the machining of whole systems in box components is crucial, as it directly affects the performance and the precision of the entire mechanical equipment. We will explore the specific application of drilling and boring processes in the machining of whole systems in box components, including the design approach of process plans, key points during the machining process, and how to optimize the plan based on actual conditions. Through this lesson, I hope you will master the process methods and techniques for machining whole systems in typical box components. In the mechanical manufacturing industry, box components are very important foundational parts. They are typically used to house and support other components, serving protective and positioning functions. The quality of the whole system machining on box components is directly related to the working precision and service life of parts, such as shafts and gears that fit with them. Therefore, the reasonable design of drilling and boring process plans is crucial for ensuring the machining quality of the whole systems in box components. Fundamentals of drilling and boring processes. Drilling is one of the fundamental methods for hole machining, typically used to create initial holes in solid materials. The drill bit is a primary tool for drilling, with common types including twist drills and center drills. The twist drill is the most commonly used drill bit, consisting of a shank, neck, and working part. The working part is further divided into the cutting part and the guiding part. The cutting part is responsible for cutting the material, while the guiding part serves to direct the drill bit and facilitate chip removal. Boring is a process used to further machine existing holes to improve their dimensional accuracy, shape accuracy, and surface quality. The boring tool is the cutting tool used in boring processes, and it can be categorized into single-edge boring tools, double-edge boring tools, and floating boring tools, depending on the machining requirements and the type of machine tool. Single-edged boring tools have a simple structure and are easy to adjust, but they have lower cutting efficiency. Double-edged boring tools offer higher cutting efficiency, but their adjustment is relatively complex. Floating boring tools can automatically compensate for tool installation errors, thereby enhancing machining accuracy. Analysis of machining processes for whole systems in typical box components. For the machining of whole systems in typical box components, process analysis is the first step. This includes analyzing the structural characteristics, technical requirements, and material properties of the component. For instance, some box components require high positional accuracy for their whole systems, such as parallelism and perpendicularity, while others may have high requirements for surface roughness. During process analysis, it is essential to select appropriate machining methods and process routes based on these requirements. Generally speaking, the machining process route for whole systems in box components can be divided into 3 stages: rough machining, semi-finish machining, and finish machining. The rough machining stage primarily involves removing the majority of the excess material to lay the foundation for subsequent machining. The semi-finish machining stage aims to further improve the dimensional and shape accuracy of the holes. The finish machining stage ensures the final dimensional accuracy, shape accuracy, and surface quality of the holes. Design of drilling and boring process plans. When designing drilling and boring process plans, multiple factors need to be considered. The first is the selection of tools, which should be based on the size of the hole, accuracy requirements, and material properties to choose the appropriate drill bit and boring tool. For example, for smaller diameter holes, a twist drill can be used for drilling. For larger diameter holes, a drill bit can be used to create a pilot hole, followed by boring with a boring tool. Secondly, there is the selection of cutting parameters, which include cutting speed V, feed rate F, and depth of cut AP. The cutting speed V refers to the linear speed of a point on the cutting edge of the tool relative to the main motion of the workpiece. The formula for calculating V is pi multiplied by d multiplied by n divided by 1000, where d is the diameter of the tool or workpiece in millimeter, and n is the rotational speed of the tool or workpiece in revolutions per minute. The feed rate F is the displacement of the tool relative to the workpiece in the direction of the feed motion, measured in millimeters per revolution, feed per revolution, or millimeters per minute, feed per minute. The depth of cut AP is the depth at which the cutting edge of the tool penetrates the workpiece, measured in millimeters. Selecting appropriate cutting parameters can enhance machining efficiency and quality while reducing tool wear and machining costs. Additionally, the selection of machine tools and the design of fixtures must also be considered. The choice of machine tools should be determined based on factors such as machining accuracy and production volume. For instance, CNC machines can be selected for high-precision small batch machining of whole systems in box components, while specialized machines may be chosen for mass production. The design of fixtures should ensure accurate positioning and reliable clamping of the workpiece, while also facilitating easy loading, unloading, and adjustment. Typical case analysis. Let's further illustrate the design and application of drilling and boring process plans through a specific case of machining whole systems in a typical box component. Suppose we need to machine a gearbox housing, which includes multiple hole systems such as the main shaft hole, input shaft hole, and output shaft hole. These hole systems require high positional and dimensional accuracy. First, we conduct a process analysis of the box component. Based on the past drawings and technical requirements, we determine the machining sequence and methods for each hole. Generally, the reference surface is machined first, and then the hole systems are machined using the reference surface as the positioning datum. For critical holes like the main shaft hole, a drilling followed by boring process can be employed to ensure the accuracy of the hole. Next, we select the tools and cutting parameters. For drilling, an appropriate twist drill is chosen, and the cutting speed and feed rate are determined based on the hole diameter and the material properties. For boring, a suitable boring tool is selected, and the cutting parameters are similarly determined according to the machining requirements. In terms of machine tool and fixture selection, considering the high precision requirements for machining this box component, a CNC machine is chosen for the operation. A specialized fixture is designed to ensure accurate positioning and reliable clamping of the box component during the machining process. During the machining process, it is crucial to strictly follow the process plan and pay attention to controlling the machining quality. For example, during drilling, ensure that the center of the drill bit coincides with the center of the workpiece to avoid deviation. During boring, it is important to adjust the cutting edge of the boring tool to ensure the dimensional and shape accuracy of the hole. At the same time, we must emphasize the system's engineering perspective and professional competence. When developing a comprehensive hole machining process specification, it is important to recognize that each process is interrelated and influences one another. For instance, the quality of the drilling process will affect the subsequent boring process. This requires us to think from a holistic perspective, rather than focusing solely on the machining quality of a single process. In actual production, a team is often needed to complete the machining tasks for box components, including process designers, machine operators, and quality inspectors. This necessitates a sense of standardization and team collaboration, with everyone strictly following the process specifications to collectively ensure machining quality. Optimization of process plans. In the actual machining process, it is also necessary to optimize the process plans based on the machining conditions. For example, if a particular process is found to have low machining efficiency, adjustments to the cutting parameters or a change of tools may be considered. If machining quality is found to be unstable, the causes can be analyzed and appropriate measures taken, such as adjusting machine tool precision or improving fixture design. Additionally, with the continuous advancement of technology, new machining techniques and process methods are constantly emerging. We can pay attention to these new technologies and methods and apply them to the machining of whole systems in box components to improve machining quality and efficiency. For example, using high-speed cutting technology can increase cutting speed, thereby enhancing machining efficiency. Employing advanced tool coating technology can improve tool wear resistance and cutting performance. In this lesson, we focused on a case study of machining whole systems in a typical box component, providing a detailed explanation of the design and application of drilling and boring process plans. We learned the fundamentals of drilling and boring, including the types, structures, and characteristics of drill bits and boring tools. Through the analysis of the machining process for whole systems in a typical box component, we understood the method for formulating process routes and the tasks of each machining stage. When designing drilling and boring process plans, we need to consider factors such as tool selection, determination of cutting parameters, and the design of machine tools and fixtures. Through specific case analysis, we further mastered the methods for designing and applying process plans. At the same time, we emphasize the importance of a systems engineering perspective and professional competence, hoping that in future studies and work, everyone can think from a holistic perspective, with a sense of standardization and team collaboration. Finally, we also mentioned the optimization of process plans, encouraging everyone to pay attention to new technologies and methods to continuously improve machining quality and efficiency. Through this lesson, I believe everyone has gained a deeper understanding and insight into the machining of whole systems in typical box components. I hope you can apply the knowledge learned to actual production